Is this on? Can people hear me?
Yes.
Okay. So first, I would like to thank the organizers for giving me the opportunity to come to Australia. I always wanted to come to Australia, so this is such perfect. And in the middle of Toronto winter, where it's like -14 today, so it's perfect. And I was asked by Charlie to talk about, so he gave me a talent geophysics in rocky earth, I think it was. So I take it to super Earth to make it a little bit more general, and it's going to be focused on what I think is the connection to habitability. In geophysics, we can talk about many things, but I'm going to try to talk about why we care about determining if planets other than Earth have plate tectonics or not. So it's basically, I'm centered around mantle convection. I'll try to be as general as possible. Stop me if I'm using any jargon, because I know that the people in the audience come from different backgrounds. So first, I want to talk about where do rocky planets come from. So as to understand the evolution, thermal evolution of this planet. So they have to start from the composition of the nebula that condenses out dust coagulates somehow to form embryos, and these embryos at some point start colliding with one another in energetic events. So we think of these events as delivering a lot of heat to the planet, so presumably they start hot, and then they either lose their atmosphere because there's atmospheric evaporation, or through the giant influx it can also lose atmosphere. And at some point, they either replenish the atmosphere, that's the secondary atmosphere that we see on the Earth, or they don't, like something like Mercury. And at the end, you end up with a planet that may or may not host life. So the reason I'm showing you this is because we believe that planets start hot. And maybe we are just not imaginative enough, but that's what we think so far. And so this is a qualitative picture of a terrestrial evolution. So planets start hot, experiencing heat flashes of 10 to the 5 watts per meter squared, under a phase that we call a magma ocean. I'll tell you a little bit more about it. So it's molten magma. It's really hot. It cools really quickly. On purpose, I left this without axis because we don't exactly know the timescale very well, but it's something around 100 million years. And so it cools down really quickly. It solidifies from the bottom up. I'll show you in a second another cartoon. And it must form the first crust. And at some point, this crust either needs to stay pristine, and therefore the planet will continue to lose heat under a satin lid evolution. So this pristine plate doesn't break or convex. Or perhaps the planet finds a way to fail this plate, and then plate tectonics can start. And plate tectonics, one of the key things that I wanted to take away from this stuff is that plate tectonics can remove heat faster than a satin lid can. But at some point, the planet will lose enough heat that it will go under a satin lid convection, and the planet will be dead, what we think Mars is now. And so the cartoon for the magma ocean, before I go to that, it could be that you have episodic transitions between plate tectonics and satin lid. And this was actually pointed out by Sleep. I'll show you a cartoon about that. That perhaps Venus might have been in this episodic regime. Perhaps the Earth might evolve into that regime. We don't know. So this is a cartoon of the magma ocean, and shows you that. So when the planets start hot, and if you have this giant impact planet that can deliver a lot of heat, you can melt the mantle, maybe most of the mantle or all of the mantle. And so you have the mantle here and you have the core. And because the temperature profile of the planet has a different slope than the solidus and the liquidus, I'll explain to you what that means. The planet solidifies from the bottom up. So the solidus, this is much more chemistry than astronomers like to think about, is the temperature at which the first melt starts appearing. So anything below, anything colder than the solidus, it's completely solid. Then anything above the liquidus is completely liquid, and you have this mush layer in between. And you have that mush layer in between because you have more than one component melting. If it was only water, you wouldn't have this. You just have one melting line, which is what we're used to. And so the planet goes into because of this, because of the geometry of the slope, then the mantle solidifies from the bottom up, and so there's magma here, and at some point that first crust is formed. And we really don't know what makes a planet perhaps fail that plate into plate tectonics. And there's been theories about it, and we can talk about it more, but I decided to not focus so much on that because it's really unknown. Now this is the story we think happened on Earth. So after that solidification of the magma ocean, the Earth somehow managed to have plate tectonics. And so this is a cartoon showing some of the complexities behind plate tectonics. And so you have a mantle convecting here and creating plates at the mid-ocean ridges, which is what you see here. It's the mid-ocean ridges where plate is being created as we speak. And then the plate thickens with time, and when it encounters another plate, the densest one has to sink. So in this case, the cartoon shows this one sinking, perhaps all the way into the cold mantle boundary, perhaps not. You can have more complicated things, but the basic idea of plate tectonics is that subduction has to happen. Subduction is not an easy thing to happen. We'll talk about it more. And one of the reasons why we think plate tectonics is important is because the exchange, the chemical exchange between the atmosphere and the interior will be different if you have plate tectonics that is bringing up material constantly in volcanism through mid-ocean ridges, ocean islands, and volcanic provinces in the continents, versus a stagnant lid where you might have some volcanism and that's it. And in a stagnant lid, you wouldn't recycle things so easily, whereas subduction plays that role on the Earth. It recycles back material that used to be on the surface back into the interior.
Excuse me, Diane.
Yeah.
Isn't it the case that if you had a bowl of any type of liquid except water, that if you cooled it on the surface inhomogeneously, you would get sinking because it would be denser than the rest of the material?
So you're cooling from
surface.
the top?
Yeah, cooling from the top.
Yes, so you do. You have that, but it has to overcome a criteria. So it has to overcome the Rayleigh number, the critical Rayleigh number. And water is a little different because water you're in a regime where viscosity is really low. So you're in a,
I thought it was just that ice is lighter.
Sorry?
I thought it was just because ice was lighter than water.
So it is. So
but everything else is heavy.
That's true. So for convection to happen, you have to have material that's light. That's light, so low density, deep, that wants to rise up, right? But it has to overcome a criteria for this kind of, I'll explain to you in a second, and it's caused due to viscosity. That's not the case for liquid water because water is pretty much invisible. Okay, so this is the Earth, and now let me show you something like Venus. So Venus doesn't have a plate that we think is failing right now. It might have had some episodic resurfacing about half a billion years ago. And so the plate here just thickens over time. The difference here is that the plate cannot continue to thicken because at some point it encounters another plate and one of the two has to subduct. Here, there's no such thing. The plate just keeps thickening and thickening over time. And then you have the mantle convecting, but the plate doesn't really go down. It's not really involved in mantle convection. And this was a cartoon showing by Sleep when he proposed that it could be episodic evolution, thinking, okay, the Earth could have started really hot. It goes through a magma ocean phase. At some point, it freezes up so that you form the crust, and it transitions maybe into plates, depending on where the radioactive heat sources are with respect to how much heat plate tectonics can carry out. You can either continue into that phase or transition back into the magma ocean. You can have this cycles of evolution, but at some point when you brought down the radioactive heat sources low enough, the planet has no other option than to go into stagnant. Okay, so why do we care again if it's plate tectonics or stagnant? And one of the reasons is, I think, at least on Earth, we think that plate tectonics is really important in regulating temperature through the carbonate silicate cycle. So the carbonate silicate cycle on Earth operates the following way. So you have carbon dioxide in the atmosphere, but if you have rain, it can interact with rock. And so you have this rock here that can interact with CO2 and water, producing this carbonic acid, leaching out these ions of calcium, sometimes magnesium as well. And then it flows through the stream down to the bottom of the ocean. And at that point, that carbon that was around, say, in the ocean can then now combine with this calcium so that you form calcium carbonates. So the carbon that you had as gas in the atmosphere gets sequestered into a rock. And then at some point when it subducts, it goes back into the cycle, into the mantle, closing the cycle because volcanoes can bring out that CO2. So that's how you close the cycle. And it's a thermostat because if you have high temperatures in the atmosphere, you have more precipitation, you have this reaction, this weathering reaction happens faster, so you bring down CO2 faster. So if you're cooler, you're going to end up bringing out CO2, you're going to end up sequestering more CO2, so you're going to bring down that greenhouse gas, you're going to cool down the surface temperature. And if you're too cold, this reaction will be too slow, you're not trapping a lot of carbon, but you are bringing them up through volcanoes, so it'll stabilize the temperature again to something lower. And on Earth, it's enabled by plate tectonics. And again, subduction is the key. Another point that I want to make is the role of water. So the carbon silicate cycle that I just explained can only happen in the presence of water. And many people think that water has allowed for plate tectonics to happen. We don't really know because we cannot experiment and have an Earth analog to take out the water and see what happens. But we do know that water acts as an agent to reduce the yield stress of the rock. I'll talk about that in a few slides. So even though the water budget on the Earth is tiny, it's less than 0.1%, is really critical for how the planet operates. And I thought about putting this slide here. I thought it was a very provocative idea that I heard from Robert Hazen from Carnegie Institute, where he asked the question, does the origin of life require some minimal degree of mineral evolution? And I would like to know from the people that study more minerals in the context of life what they think.
Yes.
Okay, that's it. So let's go into his argument. So it has to. So the planet stars are from a pre-solar grain to chondrite, so with very few minerals, about 12 minerals, and through our phases, through certain events that involve water, plate tectonics is a major one, oxidation, you end up with more than 4,000 minerals. And so perhaps at what point do you need, at what point is enough for you to have life? That would be an interesting question to answer. And if you have no plate tectonics, for example, would you hinder that? Just from the perspective of a mineral evolution, let's call it. Okay, so let's dive a little bit more into mantle dynamics. I'll try to be as pedagogic as I possibly can. Please stop me if I am failing at it. So when we try to ask, can other planets have plate tectonics, and why is it that in our solar system only Earth has plate tectonics? There are two ways of studying this. So these are the equations that govern the system. So it's an Navier-Stokes equation. You have continuity, so mass conservation, momentum conservation, and energy conservation. And these are really difficult to solve because of this nonlinear term. But in terms, it's very difficult to solve. And so you can have a computational approach where you simplify this equation, or you can have a parametrized convection. And just to go back to your question, so when we're talking a macro convection, this term is pretty high, and this term isn't. So we're in a system where we're in the low Reynolds number flow, so the inertia terms don't matter. For water, it's the opposite. For water, for gas, for what astronomers think about, there is this term, viscosity is so low, it doesn't matter. So that's why getting to a criteria for convection in water is different than getting to a criteria for convection in low Reynolds number flows. Okay, so parameterized convection is a way of bypassing this complexity and trying to get to the order of magnitude estimates of convection. So that's the first thing we did. And I think for this lecture that I can explain the basics. So this is based on classical boundary layer theory that was developed in the 1980s. There's a great book about this. And it tells you that the governing parameter is this Rayleigh number. This Rayleigh number is really what controls convection and the parameters of convection. So you can think of, if your planet is going plate tectonics, you can have a plate that thickens over time and subducts. And perhaps you would have the same thing if you have, depending on your boundary condition. So there's two ways of defining your system. You can have the system being heated from below. So if it's hot below, the things will be low density here that will want to convect up. Or you can have a system where you have radioactive heat sources there, heated from within. Again, there will be light material here that will want to convect up. The reason there's a criteria is because viscosity will really try to not let things convect. That's not the case for water. So you have to overcome some critical Rayleigh number in order to convect. The way you define this Rayleigh number is different depending on the boundary that your system is under. So this is from heated from within, like radioactive heat sources, or heated from below. So you have something, so heated from below is when you boil a pot. And the Earth is in between, actually. When I first did this study, I thought that it would be more convenient to use this sort of boundary condition, but that's not what it is. And then you can say, okay, and this is actually the critical part. You can think of defining okay, there's the proof. You can define a measure of the vigor of convection by looking at the Nusselt number, which is also a non-dimensional number, and say, okay, they're defined differently depending on the different cases. And say, okay, if you're heated from within, if the planet is convecting vigorously, the difference in temperature between the interior and the surface system will try to bring that down. If the convection is sluggish, that temperature will not be so great. It'll be something close to conductive. So that's your definition here, and it ends up being that it's the thickness of the mantle or the convective layer over 2 times the thickness of the boundary layer. You can define it differently and say, okay, I'm defining my Rayleigh number, or I'm defining my system in terms of a difference in temperature, and therefore my Nusselt number is now different because I fixed the surface temperature. I fixed the difference in temperature. And so if it's convecting really vigorously, it'll convect heat out very fast. The heat flux will be really high. Compared to if it wasn't convecting, if it's only conducting, then that would be very low. So that is a measure of the vigor of convection in this boundary.
Excuse me, the delta T is the temperature difference between where and where?
Between the surface and the bottom. Yes, I should have. And this is the crucial part of boundary layer theory. And is that the thickness of the boundary layer does not really care about how thick that convective layer is. So the thickness of this does not really notice how thick the mantle is. That is the key point of parameterized convection. So if you do that, then you know you have a one-dimensional number that's governing your system. They have to be related. You can find out the relationship here. And that argument that I just told you, you can arrive either by energy statement, or you can arrive at by looking at an infinite, a conductive layer over an infinite plane. So there is basis. I just didn't come up and told you. There is basis for that. But this very simple treatment considers that the viscosity is I should have said what it means. The Rayleigh number is equal to the density, gravity, thermal expansivity, thickness of the boundary layer, thickness of the convective layer, the heat flux out of the system, the thermal diffusivity, viscosity, and thermal conductivity. This is all assuming that the properties are one value. They're homogeneous and they're one value. The Earth is not like that. No system is that simple. So we need to think about how can we implement this in a way that we're violating any physics.
Does this work for a star too?
It doesn't, because the star is in the high Reynolds number, so it's low viscosity. So the criteria for convection is different. Okay, so once you know how the thickness of the boundary layer depends on the Rayleigh number, everything else rolls from that. You can find out the time scale for that boundary layer, because that boundary layer grows due to conduction. So it's that thermal diffusivity that's going to tell you how long it's going to grow. You can talk about the speed of the plate or the speed of the convective velocities. You can talk about the stress underneath the plate. And that stress is really important because that's what's driving plate tectonics. That force needs to be high enough to bring that plate to subduct. If it's not, you are in stagnant levitation. So the two quantities that we have to really pay attention to when we're scaling to other planets are, okay, you can think of all of them, but there's two that are really key. One that I already talked about, the viscosity, because viscosity is highly variable with temperature and pressure. So we just defined this for a homogeneous layer, and that's not the case. And also heat flux, because heat flux actually, it's a temporal quantity. Heat flux is something that I showed you before. It starts really high and then evolves through time. So whatever scaling you apply to the heat flux, you are implicitly applying a scaling to the thermal evolution. The heat flux, you multiply by the area, it gives you the heat flow, depends on two things: on how much radioactive heat sources there are in the planet and how much it has cooled or it's cooling through time. So early on, you expect cooling to be dominated perhaps by the secular cooling, it's called, and as the planet gets rid of that, it will be dominated by radioactive heat sources. And geophysicists have come up with a way of quantifying that, calling it the URI ratio. What is the contribution of radioactive heat sources to the total heat flow of the planet? And people have dedicated their life to figuring out what that number is. And I laugh because, so I'm in between two fields, astronomy and geophysics. And people in geophysics are very careful at doing this work. And I got a question one time at Fred Ratio, because I was telling an audience that some people say it's 0.8, some people think it's 0.5, and he just said, oh, it's order of magnitude 1. Because astronomers would say that. And in reality, for what we want to explore, it's of order of magnitude. Yeah, and people would not like me saying that out loud, because really there's a lot involved in calculating this ratio. It's a lot involved in calculating the thermal evolution of a planet. But for simple scaling, this is fine. This is saying order 1 is fine. Now, the radioactive heat sources on the planet, how do we scale radioactive heat sources on the planet? That's a good question. So the radioactive heat sources on Earth, acting right now, are the long-lived ones. So it's uranium, thorium, and potassium. And I really like to talk about Mark because basically it gives me more ammunition to justify that this ratio, there's a peak in the distribution of these ratios. Oh, but I can now also see that there's a distribution. But one important thing when we're scaling to other planets is that this potassium 40 is actually very volatile. So it's not only important that it's available for formation, but it's that it can be incorporated in the planet easily. And being volatile means that it might not be so easily incorporated in the planet. So that's something that can vary among different planets. So how do you scale heat flow to other planets? The easiest thing to do is to scale radioactive heat sources by mass and assume something about the URI ratio, which is assuming something about the evolution. So we did that. I'll show you the results in a second. The other thing that I want to talk about is viscosity. And so viscosity can change of orders of magnitude depending on temperature and pressure. So this is a diagram of temperature and pressure for planets that are rocky between from 1 to 10 times the mass of the Earth. And you can see that the pressures that it can achieve are 10 megabars. Thank you. The temperatures can be a little bit less than 10,000 Kelvin. And so the viscosities can vary by orders of magnitude within the mantle. And remember, I just showed you a classical boundary layer theory that assumes it to be constant. So we modified that and obtained a few results. And so if you just assume that that it scales with constant, so this is an Arrhenius law. So this is viscosity changing with temperature and activation energy. And the activation energy, enthalpy, which depends on activation energy and the pressure times the volume. And so it really depends a lot on how these change with pressure when you want to know the viscosity, and it's not really well known. That's the bottom line of this plot. It's not really well known. But because of pressure, we expect things to be very viscous on the bottom, very viscous, very hard to move. So with that simple scaling, we were able to obtain that. So how do these other parameters scale with mass? And one of the key things that we found is that the drop in temperature in the plate doesn't change very much. So therefore the temperature are at the bottom, therefore the viscosity right underneath the plate doesn't change very much. So this guy here, which we didn't know how it's going to affect the stress that could drive plate tectonics, actually doesn't change very much among the different planets. But the gravity changes, it increases, the heat flux increases because of radioactive heat sources, and the density increases somewhat because of pressure as well, compressing. So we found out that the plate thickness decreases with size. So if you scaled up the Earth to a larger version, the thickness of the plate will be thinner, it will decrease, and the shear stress underneath would increase. So from that simple treatment, we would assume that perhaps plate tectonics is feasible in other planets. Now, that was a first order approach, but once other papers came out with the opposite conclusion, we looked a little bit more carefully. Because, okay, yes, you have more stress underneath the plate, but that doesn't mean that it translates to actually failing the plate. So this is a diagram that shows you that the plates have to fail and what kind of stresses they need as a function of depth. And so you need to now look exactly what happens at the fault. And so you need to know exactly the stress at the fault and compare it to the strength of the fault. So this is the strength of the fault. So if the stress is higher, then you can subduct. If it's not, then the plate is too strong, it will not deform, it will not subduct. And so it really is a simple treatment. This Coulomb failure is just, for the ones that remember physics 101, and you have a sliding block and you try to figure out what's the friction force, and it depends on the normal, it's the same thing. You have a normal and the friction force is some friction coefficient. And this friction coefficient gets lowered by the amount of water. This is where water comes in. Water decreases the effective friction coefficient so that it lubricates the faults.
How much do you need? Half as much as Earth, or 1/10 as much as Earth?
So we don't. So the more you put, the better, until you fill out pore pressure. But let me tell you that there's something we don't know before that I cannot answer the question correctly. So and there's other treatments for how plates fail. So one study is supposed in 2012, and so you can look at how stress increases with mass, and the power that super Earths have is that because the plates are thinner, there's this factor here that depends on the length of the plate. This would be the length of the plate over the thickness of the plate, and because the plates are thinner, they get amplified at the fault. So if you go through the scaling, and you can have basal heating, which is heated from below, or internal heating, and you can think of the radius of scaling as mass to the 1/4 as a general rule, because once you include compression effects, it deviates from 1/3, and you see that that ratio that needs to be more than 1 increases with mass or increases with size. So given all the conditions that are the same for Earth, if Earth has plate tectonics, then this simple scaling would say that plate tectonics could be feasible for other planets. But the one thing that we don't know, thank you, at all, is this is a very simple treatment. If I need to go to a coefficient of friction of about 0.2 to get to values of this stress release that match the earthquake data. So this is the size or mass of the planet as a function of stress. And so this is the shear stress that overcomes the strength of the fault. This is when it's wet, and this is when it's dry. But I have to pick a coefficient of friction that is really low. Laboratory data has a coefficient of friction of 0.8. So there's a disconnect. We don't really understand all the numerical models that you see have some coefficient of friction that is ad hoc because we don't really understand it. So I have how many minutes? Okay. So I just want, so there's a series of papers that I can talk about, and I have them here, but I won't have time, so I'll pick a few. I'll pick this one because it came at the same time and it started the controversy about really are plate tectonics, is plate tectonics feasible or not for super Earth? And this study was based, it's actually Franco-Australian will be here in the talk, so in the workshop, so I'm happy to talk to him. Because what they find is actually the opposite. They did a numerical study, and numerical studies can vary in complexity from 2D to cylindrical to 3D. And what they changed is the scaling factor, the size of the planet with respect to the size of the Earth. And for the Earth, they find what we find classically. So you have an upwelling, you have these are velocities, negative velocities that way, positive velocities that way, you have a mid-ocean ridge. But then once things start increasing that factor, you start now getting episodic, you see that boundary not really connecting to the mantle, and then at some point, you really have a stagnant lid. And so what they found here is the opposite. As you increase size, you're more likely to be stagnant lid unless you reduce the yield stress a lot. I think that part of the reason is because the scaling that they did, remember going, how do you scale that Rayleigh number is really important. It's probably very different than the way we did. So assuming something about thermal evolution differently. This is another paper by Korinaga, where he did numerical studies as well. He varied the difference, viscosity is so important. So if you'll see it in a parameter over and over. The difference in viscosity between the plate and the mantle as a function of the Rayleigh number, and he obtained which ones had plate tectonics and which ones didn't, and he said, aha, as a function of mass, the Earth is here, and these planets are actually more likely to have plate tectonics, but look at how small the coefficient of friction has to be. If you look at higher coefficient of friction, Earth doesn't even get plate tectonics, even though the other ones are more likely, none of them get plate tectonics. So the most important factor he thinks is water. I'll skip this one for the sake of time. This is another cool way of looking at how plates deform. So not really looking at the Byerlee criteria and Coulomb criteria, but looking at grain size and how things get damaged. They also obtained that plate tectonics can happen for super Earths more likely. This is a work by Semenkovic, Vlada, where he looked at a parameterized 1D model, incorporating the pressure changes in viscosity that he compared to a numerical model he found. So you see here temperature, velocity, check that number. So you see the velocity here being black, and it moves almost nothing. So in the lower mantle, you really have such viscosity that you don't convect at all, so that hinders plate tectonics. But I would agree, I would argue that you don't ever get into this regime because you start from a hot planet. So this is a study following up on that by Tackley, where he looked at this pressure effects, thank you, and he has viscosity changing with depth, and you see the viscosity here could get to really high values compared to the Earth, but you have plate tectonics all the way through. And the reason is because, and there's another thing about plate tectonics that I would like you to take away as a message, is that there's something called like the tosser effect. And it's, if the planet is too cold, the viscosity, sorry, if the planet has a really high viscosity, it won't convect, but it's trying to get rid of its heat. So it'll heat up. That difference in temperature will make the viscosity lower, and it'll convect. and you go the other way around in the other direction. So there's a stabilizing mechanism where the viscosity will probably adjust that you convect the heat that you need to get out of, to get rid of. And so to end, I would say that we're just beginning to scratch the surface, really, to understand this. Looking at super Earths, even though we might not be near observing this phenomena, has pointed out some of the deficiencies in our own modeling for the Earth and the terrestrial planets. So we need to work out those things. And other things that have been to some extent considered and could be considered more as the effect of extent the role that continents play, or the core size, or impact craters in creating that initial crust, tidal heating, different chemistry. We don't really know what other planets can look like. Planets that are totally locked will have a permanent day set and a permanent night side. What would that do? So in summary, I would say that solid planets evolve habitable conditions, so we need to understand this habitability. We don't have a handle yet on plate tectonics. I would say, I'm biased, but I would say that we are converging towards thinking that plate tectonics can be feasible in super Earths. And because it's tied up intimately with the atmosphere, we need to figure this out when we're trying to interpret the spectra of planets around other stars. So thank you. I'll take questions.